Well, we learned about enthalpy in Chem 1A. Could we use that for the chemical potential? So we learned that at constant pressure, heat was equal to the change in enthalpy. So if we used enthalpy, that would predict that all exothermic reactions are spontaneous and all endothermic reactions are not spontaneous. Is that true? No. Some endothermic reactions are spontaneous. Those instant ice packs you have like in a first aid kit, you break the little seal in there and mush the stuff all together and it gets cold. That's an endothermic process. It's pulling energy in from the surroundings, and yet it is spontaneous. So enthalpy is not the answer. Here's a couple of processes that involve an increase in enthalpy rather than a decrease. So here we have an ice cube melting. We are above 0 degrees Celsius. The ice cube is going to melt. Right? What is happening to the molecules? Well, in the solid, the molecules are all very well ordered, and in the liquid, they are all jumbled. When this transition occurs, we get an increase in something called entropy. When water, liquid water, evaporates, or when sodium chloride dissolves. So here's water evaporating. We go from the water molecules being really close together to being all spread out. The silver chloride dissolving, we go from very ordered and close together to disordered and spread out. What's happening? All of these have an increase in entropy. The amount of disorder or randomness is increasing in all of these processes. So entropy is the criteria for spontaneity. And informally, we can think of entropy as disorder or randomness. And it's like, why does your house look like such a mess? Entropy. Because the entropy of the universe is increasing, and I just decided not to fight nature anymore. Hey. You take a deck of cards and you toss them up in the air. Do they land in a nice pile? No, they spread out and a big mess, right? Entropy increased. The leaves on the trees that are ordered, right? Depending on the type of species of plant, they have leaves that are opposite each other or staggered, or there's all these different differences, but there's order. When the leaves fall to the ground, do they land in a nice ordered manner? No, they blow all over the place, right? Entropy is increasing. So that's the informal way of thinking of entropy. So, of course, we have to talk about what exactly is entropy. Entropy is given the symbol capital S. Don't ask me why. I do know that E was taken by internal energy, so we couldn't use that. So it's S. It's just, we have to deal with it. So this is a thermodynamic function. It will increase with the number of energetically equivalent ways to arrange the components of a system to achieve a particular state. I don't expect that to have made any sense. Hopefully, after a few slides, it'll make some sense. We can say that entropy is equal to a constant times the natural log of W. The constant here is the Boltzmann constant, and W is the number of energetically equivalent ways to arrange those components. And we're going to get to what that means. The units of entropy are joules per Kelvin. Okay. So let's imagine an ideal gas, a fixed amount of it, and we've got constant pressure, constant volume, constant temperature. The state of that system is defined by pressure, volume, and temperature. The energy of that system is constant. It's not changing. But where the energy is at any given instant is not constant because those gas particles are moving around. And they're changing their energy. We can think about the average kinetic energy is going to be dependent on the temperature. But some of them are moving fast and some of them are moving slow, and they can change. right? They bump into each other, and one might end up being slow after that and the other one fast. So at any one instant, a given particle could have a high kinetic energy. In the next instant, it might collide with something else and now have low kinetic energy. So there's different ways for this system to be arranged. The state or the macrostate is the big picture. The microstate is looking at the exact internal energy distribution among particles at any one instant, like a snapshot of what's going on. This is not something that we can actually directly observe, so it's more of a thought experiment. But any given macrostate can exist as a result of a large number of different microstates. The macrostate stays constant while the microstates are changing. The energy is redistributing itself, but the overall energy is the same. So we can think of W as the number of possible microstates. So we're going to look at some simple examples. A system with two particles. We have system A, it's got two particles. System B also has two particles. Total energy of both systems is 4 joules. In the first system, there's only one energy available to these particles, and so they are both 2 joules. In system B, there are 2 different levels available, 3 joules and 1 joule. And so for a total energy of 4 joules, one is going to be in the low energy state and one's going to be in the high energy state. But these particles are different, even if they are the same identity, right? Even if they're both neon atoms, they are still 2 different atoms, right? You talk to identical triplets, it's like, okay, these 3 people are genetically identical. Does that mean they are interchangeable? No, they are 3 individual people, right? So atoms are like that as well, particles. So these are 2 different particles, even though they may be exactly the same. So we could have the red one being at the high energy, the blue one at low energy, or we could have the blue one at high energy and the red one at low energy. Is the macrostate the same? Yeah, the total energy is still 4 joules. Total energy, 4 joules, but there's 2 different ways to distribute that energy. Yes?
So would that mean W is 2?
Yeah. So for system B, W would be 2. There's 2 possible ways. Okay, that makes sense? So because there's more microstates, system B has greater entropy. So we talk about W, and W can represent possible microstates. We're not actually ever going to deal with numerical values of W. It's more understanding the idea. So the entropy increases with the number of energetically equivalent ways. That means we're going to make these different, arrange the different components, but still we'll have the same overall energy. The more ways that you can arrange with the same energy, the more entropy. We can also think of it as dispersal of energy. So the state with the highest entropy also has the greatest dispersal of energy. Energy tends to spread out. It doesn't want to be confined. So when we look at energy, the energy of system B, it's dispersed over 2 levels. So some of the energy is this level, some of the energy is that level, where here it's all in one. So this is spread out. It's just spread out. So a state where we have the energy being more dispersed or randomized has more entropy than when that energy is more concentrated. So, I mean, think about a Bunsen burner, right? We boiled a bunch of water the other day. Does all the energy given off just stay right there by the flame? No, it spreads out, right? And gradually, the whole room got kind of warm, right? With all these Bunsen burners going gradually. Depends on your point of view. At least the AC was working, because I did this once when the AC was not working, and it was 94 degrees in here.
I would have just not in the lab.
Yeah, I wanted to, but I had to stay. It was bad. It was bad. Okay, we said we were going to get to the second law of thermodynamics. Here it is. For any spontaneous process, the entropy of the universe increases. This is not necessarily the entropy of the system, it's the entropy of the entire universe. Okay, so the criteria for spontaneity is the entropy of the universe. If something causes the entropy of the universe to increase, it will be spontaneous. Yes?
Can you say that 3 times fast?
No, I probably can't say that 3 times fast. I don't know if I can say anything 3 times fast. Entropy is a state function. Remember what state functions are? The example in Chem 1A was people climbing a mountain. The change in elevation is a state function. It doesn't depend on how you got from the bottom of the mountain to the top of the mountain. It just depends on where you started and where you ended up. And the illustration had some people going up, a path with a lot of switchbacks, and other people kind of climbing straight up the side of the mountain. They traveled different distances, but the change in change in elevation was the same. The way I prefer to get to the top of the mountain is to get into a helicopter and have it go straight up and over and just deposit me on top of the mountain. My elevation change is exactly the same as the people that hiked up, right? A state function only depends on final and initial state. Beam me up, Scotty, yeah. So the change in entropy is going to only depend on the final and the initial states. So chemical systems will proceed in a direction that increases the entropy of the universe. So let's look at this gas, 4 particles, and there's a stopcock here, it's closed, and on the other side is nothing. This is a vacuum. There's nothing over there. So if this gas is expanding into the vacuum, expanding against a pressure of 0, remember we had a kind of work that was negative P delta V. A pressure expanding against, a volume expanding against a pressure does work. Here, because there's no pressure, no work is done. So the energy is not changing. But the entropy changes when these particles with their energy spread out. So after we open the stopcock, they could all just stay over here. All the particles could move to the other side, or we could have half and half. There are a bunch of other possible states, right? But we're only going to look at 3 for simplicity. So how many possible microstates does each macrostate have? Well, how do we think about this? Here we have to think about these atoms are identical, but they are individuals, and so we're going to label them 1, 2, 3, 4. So here, for state A, this is its macrostate. The microstate, all 4 particles are still over here. There's no other way to arrange them, right? They're all over here. In state B, all the particles were on the right, and again, all the particles are on the right. There's no way to rearrange them, and so there's only 1 microstate possible for state A and B. When we get to state C, we have 6 different microstates. So in all of these, we have 2 particles on each side. But which 2 particles? So here we have 1 and 2, and 3 and 4. But we could also switch those, like down here, they've just completely switched sides. Here, 2 and 3 versus 1 and 4, and that one is completely opposite of this one, and then these 2 are opposite of each other. There are 6 different ways that you can arrange those particles, having 2 on each side, but different ones. So the probability of finding atoms in state C is 6 times greater than in state A or B. This is higher entropy. It's favored. It's more spontaneous. Any questions? If we go from 4 atoms to 20 atoms, we go from 6 microstates to 184,756 microstates for state C, where we have equal atoms on each side. And yet, states A and B, where we have all the atoms on one side or the other, those still have only 1 microstate. So the entropy, when you have those particles spread out over the entire available volume, the entropy is much higher. So we see that the entropy change from state A to C is positive. So the final entropy, where we have atoms distributed in both flasks, is higher than when all the atoms were in one flask. So the change in entropy is positive, the entropy is increasing, and thus we expect the gas to spread out and not just to stay in one side. Any questions? Another way to think of this is that when the atoms are confined to one flask, their energy is confined. When we allow the atoms to spread out in that larger volume, their energy is spread out. So energy is being dispersed, it's spreading out, and that's going to be an increase in entropy. So this second law explains some things that are not explained by the first law. So here we have some water, room temperature water, and we put some ice in it, and what happens? Well, we know from experience that heat energy from the water goes to the ice. Heat flows from higher temperature to lower temperature. The first law of thermodynamics does not prevent or prohibit the concept of energy going from the ice to the water. That would mean that the ice gets colder and the water gets hotter. We know from experience that that just doesn't happen. But the second law explains why that doesn't happen. The water has more energy than the ice, because it's a higher temperature. And when the heat goes from the high temperature to the low temperature, it spreads out, right? That's an increase in energy dispersal, an increase in entropy. If heat went from the ice to the water, then the heat would be becoming more concentrated. The energy would be more concentrated, and that is not a spontaneous process. Any questions?